coordinate proofs. Half the battle of performing a coordinate proof is finding or figuring out how to place your figure. So let's look at example 1, and we'll just kind of work this as we go along. Example 1 asks us to prove that the midpoint of the hypotenuse of a right triangle is equidistant from the 3 vertices. Now, that's a lot of big stuff in there. Let's just start by placing our right triangle. So if we want to place a right triangle on a coordinate axis, it helps to put the right angle at the only right angle on the graph. So that's a good way to place a right triangle. Now let's label the vertices. This one's obviously 0, 0. Okay, we'll call this, just to follow the book, we'll call this C, B, A. Now, this has an x value, but we need a variable because we don't want to show that it's true just for a specific x value. We want to show it's true for any x value. So we'll call it A. It has a y value of 0. And similarly, this one will be 0b, having a 0x value and some random y value. Now we want to prove that the midpoint of the hypotenuse. So let's look at the midpoint. We'll call it D. And using our midpoint formula, we know that it has to be A over 2, B over 2. And we want to prove that that is equidistant from the 3 vertices. Okay, so already we've done most of the work. What we want to do is we want to show that D is the same distance from A, B, and C. Now, I'm not going to do all the work for you. I'm going to let you kind of work this on your own. I'm just going to walk you through the steps here. If D is our midpoint, we want to show that this distance is equal to this distance and is equal to this distance. So what would we use to compare those 3 distances? The distance formula. Now I'll do one of them just because I want to show you this. If we're plugging it into our distance formula, let's use dB. We don't have to go too far in simplification here. We take the difference of our x's and square it, a over 2 minus 0 squared, and the difference of our y's, b over 2 minus b squared. We get a over 2 squared. B over 2 minus b is negative b over 2 squared. This is a squared over 4 and b squared over 4, which already have common denominators. So it's a squared plus b squared over 4, which is equal to the square root of a squared plus b squared over 2. Okay. So that's what our final product will look like for the distance between B and D. And you might even be able to stop right around here or here, because you're going to come up with similar things when you're finding DA and DC. So all you have to do is go just far enough to prove that they're all the same. You don't have to get a perfectly simplified radical. Let's look at example 2. Example 2 wants us to prove that the median of a trapezoid is parallel to the bases and has the length equal to the average of the length of the bases. So a trapezoid, got to be careful that we're not drawing a rectangle or a square. We got one base, we've got another base with some random length, but it has to be parallel to the other base. Let's mess that up a little bit. This is a little too neat. There we go. Now it doesn't look quite so isosceles. Again, let's label our axes. I'm going to diverge from the book a little bit. Here's where it gets a little tricky. D has to follow some variable for the x and 0 for the y. B and C have to have the same y values because they have to be, BC has to be parallel to the bottom, so it has to be perfectly horizontal, so we got to match those y values. But they have to have different x values. And those x values shouldn't match A or D because that would give us a right angle. That'd be kind of cheating a little bit. So let's just call these B and C. So what we want to do is construct the median, which connects the midpoints of B and C. Okay, so here's, call this M, this N. This has got to be B over 2 and K over 2 using our midpoint formula. This would be C plus D over 2. Sorry, not C plus D over 2. yes, C plus D over 2, K over 2. So this is my median of my trapezoid. I want to show that it's parallel to the bases. So first thing I need to do is show that it's horizontal, okay, by just calculating its slope. And then I want to show that its length is the average of the lengths of the bases. So I need to find the length of AD and the length of BC, add them together and divide by 2, and compare it to the length of MN using my distance formula. So it's very, very similar to the previous example. The nice thing is my distance formulas are going to clean up nicely because they're all horizontal lines. And so really the distance formula for each of these, when I subtract the y's, I get 0. And so it's going to be really straightforward for the distance formula. But I'll let you work that out. Last example, example 3, we'll walk through this just in a little more detail than the last couple. We want to prove that the altitudes of a triangle meet in one point. That is, they are concurrent. So first of all, remember that an altitude is drawn from one vertex perpendicular to the opposite side. Now, here's where they mess with you a little bit. Normally, when I'm drawing a triangle, I start at the origin and just draw one leg like this and work off like that. What they do is they put one of the vertices straight up on the y-axis and draw a little more random from there. And in this case, that actually works with altitudes, because what that does, since we're drawing perpendicular to the base, that makes one of our altitudes follow the y-axis perfectly. So that's probably the only reason we'd want to do this. So let's label our vertices A, B, C. So B is some 0B. A is some A, 0. And C is some C, 0. Now notice I didn't put negative A. I'm just going to deal with regular A, and we don't have to worry about the sign so much. Okay. So when I draw my altitude from A to the other side, it's drawn perpendicular to BC. And yeah, we're going to have to kind of find an equation for that based on our variables. And altitude here is drawn perpendicular. So what I want to do is I want to show that these all intersect at the same point. That's the fun part. Which means I need equations for each of these. Okay, so let's call these T1, T2, T3. So for T1, my equation is simple. It's x equals 0. That's my line. Okay, and so that's what makes this that much easier and with the way we constructed it. So in order to find our equation for T2, we need our slope for AB. Now, our slope for AB we found by doing B minus 0 over 0 minus A, which gives us negative B over A. So our slope for T2 has got to be positive A over B. So when we plug that with the point into our equation, we got 0 equals A over B times C. That's using this point right here with our new slope to find our intercept. And so our intercept has to equal negative AC over B. So our equation for T2 is y equals A over B x minus AC over B. Okay. Now, for T3, the slope of BC would be B minus 0 over 0 minus C, which is negative B over C. Which means for T3, we take the negative reciprocal, because we're looking at perpendicular lines, remember, we get C over B. So when we combine that with the point A0, we have 0 equals C over B times A plus our intercept, which means our intercept has to be negative AC over B. So for T3, we get the point y equals c over b x minus ac over b. So notice that for T2 and T3, both of them have a y-intercept at 0, negative ac over b. And that point is also on T1 because it has an x value of 0. So that's where all of those altitudes intersect. That means they all meet at the same point and are concurrent. So that's how we use coordinate proofs. We use variables in place of numbers, and we use algebra to arrive at a proof rather than having to walk through geometric proofs and two-column proofs and all the stuff you did there. All right, so if you have any questions, feel free to ask. You can go back and watch the video again if you need something clarified. Otherwise, you can start on your homework.